We are on to question 18, and question 18 is a closed pipe question. This is a pretty straightforward knowledge question, and it's simply asking, it says, tuning fork A, and this question actually would make much more sense if we did the lab for this, but you're just gonna have to use your knowledge of closed pipes. And let's review that before we do the question. Let's review open, closed pipes and fixed strings. And the premise of closed pipes is that in a closed pipe, the shortest wavelength that will produce a node right here, which means complete destructive interference, so no sound, and an antinode at the opening. That shortest wavelength is 1/4 of a wavelength. So 1/4 of a wavelength in a closed pipe will produce the fundamental sound, we call it the fundamental pitch, is the shortest wavelength you can have in a closed pipe. After that, everything just increases by half a wavelength. So the next one is going to be three-quarters of a wavelength, and so on. So for closed pipes, they're 1/4, 3/4, 5/4, 7/4, and so on. For open pipes, you must have antinodes at both. Since they're both open, you must have antinodes at both. And the shortest wavelength that fits in an open pipe is half a wavelength. And then once again, they increase by half a wavelength each time. So the next one will be 1 wavelength. And so on. And for fixed strings, it works the same way as open pipes, because on fixed strings, you must have a node on both sides, and so the shortest wavelength you can have is a half, and then it follows the same pattern. Okay, so this question is just a knowledge question on, do you understand the principles behind closed pipes, open pipes, and fixed strings? This one's a closed pipe, and it's saying, so it says you put the tuning fork on and the sound gets louder and then softer and louder. Obviously, the loudest sounds represent the antinodes. And when there's no sound, it represents a node, because then if there's no sound, what's happening is, that's what's happening. You're getting a node at the opening, and therefore there's no sound. So which of the, in terms of wavelength, which series of numbers represents possible values for the length of the pipe? It's going to be 1/4. Well, given that we've discussed it a lot, it's obviously that one. Closed pipes are 1/4. They're right here, 1/4, 3/4, 5/4, 7/4. All right. Number 18, Doppler effect question. Oh, this is 19. Doppler effect question. A police car with a siren has a frequency of 525 hertz, is approaching you at a speed of 35 meters per second with the siren on. So as it's approaching you, are you going to hear the pitch of that siren go up or down? Well, since it's coming towards you, the sound waves are going to hit you more frequently, therefore you're going to hear a higher pitch or a higher frequency. Just get that in your head before you do the question, that the answer automatically has to be higher. Now, since all the answers there are higher, then, well, you should have figured that out, and unfortunately means you can't eliminate the answers right off the bat. Okay, so we've got the frequency of the source. We've got the velocity of the source. And we've got the velocity of sound in air on that particular day was 342 meters per second. And so we're going to use the Doppler effect equation. We simply have to decide if we can use a plus or a minus. And since it's approaching you, you use the minus. So here's the Doppler effect equation. So what we're solving for here is the apparent frequency, and we just designate that as F. So there's that Doppler effect equation. We've got all the values. We just have to decide if it's plus or minus. If it's approaching you, it's going to be a minus, because that will make that number on the bottom smaller, and therefore it will end up making this number bigger, which we want. So and you can see right here, if that was a plus, then this number at the bottom would be greater than 342, and 342 divided by a greater number is going to produce a number that's less than 1, and then when you multiply it by 525, you'll get a smaller number. So there are lots of ways you can intuitively figure out if you're doing this correctly or not. Stick in all those numbers, and you end up getting an answer of 585 hertz. C. Number 20. This is another Doppler effect question. The speed of sound in air is 326. What is the speed of a plane of the frequency U here for its engines is 0.865 times the true frequency. Okay, this is a great question. This is a good question because it appears there's not enough information. But it's just a ratio. They've given you a ratio. And so anytime they give you a ratio, you can just make up numbers for what they actually are. So it says we want to calculate the speed of the plane, but we don't have F or Fs. So the question doesn't give us either of those, but it does give us a relationship between them. It says the speed, says the frequency you hear for its engines is 0.865 times the true frequency. So you got to think about this. So, well, first of all, I'm just going to make up the simplest numbers ever. I'm going to say that the true frequency is 1, and therefore the apparent frequency is 0.865. As long as they've given you that relationship, you can put any numbers you want. You could put 10, and then this number here would be, if you put 10 down here, this number here would be 8.65, right? You just multiply 10 times 0.865. Then you need, the difficult part of this question, I think, is determining, is it a plus or is it a minus? Is it a plus or is it a minus? And you're going to say, well, if this was the frequency, the true frequency, but I hear this frequency, which is lower, then it must be moving away from me. I'm hearing a lower frequency, so it must be moving away from me. Therefore, I have to use a plus. Okay, so let's get our formula. And we are solving for the velocity of the source. Now, this is one of those, I'll go through how to manipulate this formula, but the Doppler effect formula is one of those ones where it's most of the time, if you're not solving for one of the obvious, if you're not solving for F, it's easier just to plug the numbers in and then solve for the unknown variable rather than manipulate the formula. So let's do that, and then I'll go through the manipulation of the formula just so you can see, but you'll see sometimes it gets a little tricky, especially if you're solving for V, it gets very tricky. So 0.865 equals 326 over 326 plus V times 1. So this one worked out quite nicely by just plugging the numbers in, because that 1 becomes completely irrelevant. And then all we're going to do is we're going to switch, or we're going to cross multiply. I'm just going to do this. I'm just going to switch those two. So it'll be 326 plus Vs equals 26 over 0.685. Or you can just say you just multiply them together and then you end up dividing by 0.685 to get rid of it anyway. So switching is just a little easier. And then I can divide these two and then subtract the 326 to get VS. And I'm going to get the VS in, actually I better do that. So it's going to be 326 divided by 0.865 equals minus 326 equals 50.9. That's in meters per second. Multiply that by 3.6 and you get 183 kilometers per hour. B. All right, now very quickly, if you did want to manipulate this formula, this one's not too bad. It's going to be this. F equals V plus V. So you're solving this one for VS. Probably the easiest thing to do here is to divide both sides by this. So you get F over Fs equals V over. Then you can cross multiply and divide. So let's just cross multiply. Let's do this one step at a time. Then you divide by F, so you get and then you can end up subtracting that velocity. So that's how you would manipulate that formula. And it's not insanely difficult, but I think it was way easier just to plug the numbers in and solve from there. All right, let's try and get a couple more in. A pendulum takes 2.5 to swing from right to left. What is the frequency of its oscillation? This is very similar to the first question that we did. 2.5 seconds to go from right to left. So therefore, 2.5 seconds is half of its period. Therefore, a full period would be 0.5 seconds. And they want the frequency. Frequency equals 1 over 0.5. That's an easy question. 2 is the answer to that question. If you didn't get it, refer to example number 1. It's very similar, except for it's only quarter. This one, though, we'll need to spend a little bit of time on. Mass, a pendulum. M has a mass of 4. Pendulum, the bob attached is 2.5, is pulled sideways, still makes an angle of 9 degrees with a vertical. Pendulum M is 1.5 length of string, has a mass of 1, is pulled to an angle of 90 degrees. Which of the following is true for the restoring forces? So for the restoring forces, so this is similar to one of the earlier questions too, except for they just want the ratio. So remember that this is the restoring force. This is the angle. And this is gravity. And the relationship between them is that the sine, let's just call this theta, sine of theta equals the restoring force over the force of gravity. Therefore, the restoring force equals sine theta times Fg, which is sine theta mg. So that's what you need for each of the forces, and you're just going to plug the numbers in. The length of the string is irrelevant. All we need is the mass and the angle. So M is 4 with 9 degrees. Let's do it over here. Force for M is which turns out to be the sine of 9 times 4 times 9.81 turns out to be 6.138. the sign of N, or the force, the restoring force of N is that's an easy one because the sine of 90 is 1, so it's just 9.81, and then we want the ratio of N over M. Make sure you look at the answers. The answers are in N over the top and M on the bottom. So Fn over Fm is 9.81. Divide those two numbers, 9.81 divided by 6. Is 1.59, so 1.6. 1.6. A is the answer to that question. Okay, end of this video, on to the next for the remaining questions.